do geometry of molecules and also polarity, we first want to start with our Lewis dot structures. So for CH2O, we have, we want to count the valence electrons. So we have 4 valence electrons for carbon, 6 for oxygen, 1 for each hydrogen. So that'd be 12 valence electrons, or 6 pairs. We generally should not be seeing individual electrons, so we should be seeing pairs of electrons. Only what are called radicals will have unpaired electrons. Carbon is going to be the central element. We're going to have oxygen attached and the hydrogen directly attached. And I already put in our bonding pairs. So I used 3 bonding pairs, so I have 3 more pairs to put. And nothing goes on the hydrogen. Hydrogen is complete with this 1 bonding pair. So I'll put the pairs on that oxygen. But by doing that, I've used up now my 6 pairs of electrons. But I see that I'm missing a pair on the carbon. So to get that pair on the carbon, I reach over to oxygen, steal a pair, and move it into the bond. So I have not changed the number of electrons, but now that pair is shared by both carbon and oxygen, so we counts by both. So the carbon has 2, 4, 6, 8 electrons, the oxygen has 2, 4, 6, 8 electrons. So now this is our valid Lewis dot structure. To answer electron pair geometry, we look at the electronic groups on the carbon. And we have 3 electron groups. So we're going to count the bond as electron group regardless of whether it's single, double, or triple. And then lone pairs are also electron groups. So we have 3 electron groups on this molecule, on the central atom. 3 electron groups to get as far apart as possible end up giving us a trigonal planar geometry. And since there are no lone pairs on the carbon, this is both electron geometry and molecular geometry. For the triiodide molecule, we have 7 valence electrons for each atom. That would give us 21, and then we're going to add 1 electron for the charge, so we have 22 electrons, or 11 pairs. So we're going to have iodine with 2 attached iodine molecules. So we use 2 pairs. So we have 9 more pairs. So 1, 2, 3, 4, 5, 6, 7, 8. We have completely filled up the octets in all 3 atoms, but we still have 1 pair of electrons to use up. So in this situation, we're going to put them on the central atom. Just slide that 1 pair aside, squeeze on this 2nd pair. This will, of course, only happen when we're dealing with a period 3 or higher element, period 3, 4, 5 element. So now when we look at it, we have 1, 2, 3, 4, 5 groups of electrons around that central atom. And this geometry becomes, for electron geometry, becomes a trigonal bipyramidal. And for a trigonal bipyramidal, we have now 2 different types of attachments. It has an axial position and an equatorial position. And when we replace atoms with lone pairs, the lone pairs end up on the equatorial positions. So these positions minimize 90-degree angles with each other and with other atoms. So the lone pairs end up on the equatorial positions, leaving the atoms on the axial position. So the molecular geometry is going to end up being linear. So between the N-iodine and a lone pair, that is a 90-degree angle. Between any two lone pairs here, that'll be the equatorial position, and that's a 120-degree angle. So we have 90 degrees here, 90 degrees here, so 180 between the two N-iodines, giving us a linear molecule. For geometry of the PCl5, we're going to have 7 valence electrons times 5. For chlorine, that gives 35, plus 5 valence electrons for phosphorus, so we have 40 electrons for 20 pairs. We're going to have our phosphorus with 5 chlorines attached on. Well, that already exceeds the octet on the phosphorus, but phosphorus being period 3 has access to our d orbitals, so it can exceed the octet. If we use our 5 pairs, we have 15 more pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We've used up all our electrons. We have complete octet on all the chlorines, and we have exceeded the octet on the phosphorus. So we have our 5 electron groups. So 5 electron groups is going to be that trigonal bipyramidal geometry. This is also our electron geometry. And whenever we don't have a lone pair on the central atom, our electric geometry and electron geometry are going to be the same. Two-dimensional polarity, we're going to again start off with a Lewis-Dot structure. So sulfur and oxygen both have 6 valence electrons. We're going to so 6 times 4 is 24 electrons, or 12 pairs. Sulfur will be in the middle. We stick on our 3 oxygens, use up 3 bonding pairs, so we have 9 more pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've used up all our electrons. The oxygens have complete octets. The sulfur does not. So what we're going to do is we're going to steal a pair off the oxygen, slide in, form a double bond. Now we have our complete octets for sulfur and all the oxygens. So for the polarity, this geometry is going to end up being a trigonal planar geometry. And it looks like that one oxygen is going to be different from the other oxygens, but we're going to have resonant structures, which will make all 3 oxygens identical by having that double bond migrate between all 3 oxygens. So all 3 oxygens are going to be equivalent. We have a polar bond between the oxygens and the sulfur. We have a polar bond, so will it be a polar molecule? And all our oxygens are identical. We have a equilateral, and they form an equilateral triangle. So this is a very symmetric structure. So the answer is going to end up being non-polar. And the way to check for that is if all the atoms are, if all the attached atoms are identical, and there are no lone pairs on the central atom. This makes it highly symmetric. Another way of saying no lone pairs on the central atom is saying that our molecular and electron geometries are identical geometries. So that combined with the attached atoms being identical And our electron and electron geometries are identical, meaning no lone pairs on the central atom. We have a highly symmetric molecule that even though the bond is polar, we have a three-way tug of war here and it completely balances out. So the molecule ends up being non-polar. We cannot draw a dipole arrow across this molecule. So it's a non-polar molecule.